Let's start with a sensor class most never see: Wide Area Motion Imagery. These airborne camera arrays stare at an entire city continuously through gigapixel lenses. To understand the scale, look at the collection rate. A WAMI payload takes one or two of these gigapixel frames every single second, and it keeps that up for hours. Comparing hourly data, satellite imagery is a rounding error next to WAMI's volume. Traditionally, analysts manually scrub backward through this haystack, but at the base, a flashing red node shows the analysis bottleneck overflowing. Human attention cannot scale to meet gigapixel frame rates. We've reached a breaking point where collection hardware outran exploitation software years ago. The gap between what we can record and what we can actually process is widest exactly where the sensor is most powerful. Because the sheer volume of data is so overwhelming, the hardware itself is secondary. Whoever owns the software that can efficiently read and exploit that feed owns the actual value of the entire constellation flying above it. If you want to build that exploitation software, you immediately hit a wall, getting your hands on the raw data to engineer and test your code. Real operational WAMI data is locked down. If you look at this mock surveillance interface, you can see the two main barriers: strict military classification and heavy GDPR restrictions protecting the identities of people on the ground. Trying to build a public product demo using actual surveillance footage of real people's daily movements is an immediate governance violation, especially under European law. The architectural bypass for this is to generate the data from scratch. Instead of fighting for classified footage, we build procedural, fully synthetic 3D WAMI environments as the initial engineering substrate. This synthetic approach is entirely legally clean. There are no real citizens, no GDPR data subjects to protect, and no export-controlled military imagery to manage. Stripping away that legal friction allows a single developer to write, test, and demonstrate complex tracking software in the public domain, bypassing the slow crawl of security clearance protocols. These governance hurdles serve as a forcing function. By blocking the easy path of using real data, they push modern defense technology toward a much cleaner, synthetic-first software architecture from day one. Beyond the legal benefits, working with synthetic data provides a massive engineering advantage. You get infinite, perfect labeling for free. Trying to achieve flawless annotation by manually labeling real gigapixel WAMI frames is prohibitively expensive and heavily prone to human error. This diagram shows ground truth. On the left, the system knows the exact track of every generated vehicle. On the right, an active detector tries to infer those boxes. Notice how the detector glitches and drops boxes, while the hard-coded truth remains perfectly stable. Because we control the simulation, we can build difficulty dials into the scene generator to intentionally stress test the tracking pipeline. We can artificially dial up traffic density, force the simulated camera to jitter, or deliberately drop frames to starve the algorithm of data. When we max out these dials, we manufacture deliberate failure cases. As the traffic congests, you can watch the colored tracking lines cross over each other, break, and eventually snap as the motion blurs together. Forcing the system into these edge cases in a completely controlled environment shows us the exact breaking point of the tracking algorithms. Testing these failure states against perfect ground truth before a single piece of operational data is touched enables honest mathematical benchmarking.
We rely on measurable metrics instead of anecdotal testing. The immediate technical focus for day one is simply building the foundational software harness to handle this data. This architectural flow diagram maps out the continuous data loop. Data moves from the scene generator into the sensor simulator, through a geometric detector, and finally into the tracker. When we add a fifth node for deep learning models, it remains grayed out and bypassed by the active data loop. The reasoning here is that plumbing precedes models. Advanced machine learning is entirely useless if the underlying data loop can't continuously ingest and track scenes without breaking under the load. Once that core pipeline is stable, the next question is how the software gets deployed to the end customer. We handle this through a dual custody strategy. The first option is the Sovereign Edition. It has zero external dependencies, built specifically for facilities where data legally cannot leave the premises. As this diagram illustrates, it is an air-gapped deployment surrounded by a solid wall, severing all outgoing network connections. The second option is the Governed Edition. A secondary server node outside the wall connects via regulated EU-compliant data pathways.
It runs the exact same core software, but provides the audit and compliance services that institutional buyers require. In modern defense procurement, deciding who holds the cryptographic keys and in which jurisdiction the servers physically sit is no longer an afterthought. It is the primary architectural access that dictates how the product is built. Market reality dictates the pace of change. Large institutions procure systems based on multi-year roadmaps and support guarantees, prioritizing organizational stability over code alone. This brings us to the bear case for this development model. As this side-by-side visual shows, translating perfectly clean visual terrain into a noisy, artifact-heavy real-world scan is never a one-to-one process. The risk is straightforward. If a pipeline only functions perfectly within its own sterile simulator, procurement officers will rightly dismiss it as a toy. But there is a strong bull case. European defense procurement is actively and publicly funding sovereign alternatives to closed incumbent systems. This dashboard shows a stream of accuracy metrics and benchmark graphs running right in a standard web browser. A synthetic-first, build-in-public approach generates something entrenched incumbents struggle to match: open, verifiable capability metrics. This architecture allows a procurement officer to openly evaluate the tracker's raw performance in real time, without waiting for security clearances or agonizing over complex network integrations. Transparent public benchmarking establishes an undeniable evidentiary trail. It challenges the opaque, closed-loop advantages that entrenched contractors have relied on for decades. The strategic sequence here is crucial. The synthetic pipeline is the foundational substrate. It is not the final destination. We test against perfect synthetic ground truth to establish a strict baseline of mathematical certainty. We have to know the software works before introducing the chaos of a real operational environment. You have to build the pipeline and benchmark it synthetically to earn the operational right to ingest real, classified WAMI data. Massive sensor collection broke the capacity for human analysis. Solving the WAMI bottleneck starts by mastering the artificial before we process the real.